So thank you for the introduction. It's great to be here in Belgrade. So as the title of the talk says, I'm going to talk about autonomous mobile robots and about the AI that powers those robots. What I think is really crucial to mention when we talk about Gideon as a company that I work for is that the AI is really the core product for us. So it's used in almost all layers of our autonomous stack. And, or to say so, it's not really like cherry on top of cake. It is the whole cake. So before I start talking about robots, I'll tell you a little bit about myself. So I'm purely a technical person. So I hold a PhD in artificial intelligence. And also before that, I worked for over 12 years in the industry as an R&D engineer first, and then later on as a machine learning engineer. So currently, I'm leading a product team consisting of 6 teams, mostly AI and robotics engineers. And we're developing autonomous stack for the tray autonomous forklift. So what is a tray autonomous forklift? I'm going to show you in a minute. So basically, I mentioned autonomous mobile robots. So we use them for material handling purposes. So, and we also use computer vision as our primary sensor. So basically, you might ask yourself, why material handling? I mean, there's a lot of cool applications that you can use robot for. So we all live in the era of Amazon, and you order something today and it already comes tomorrow to your home. And while you're sitting like really comfortably in your couch, someone else is doing the heavy lifting in the warehouses. And also, all these jobs in warehouses, they are pose a risk to human health. So for instance, someone would have like problems with the spine in their old days. So what we're trying to do is really automate these jobs, and really, you know, it's not really excited. So for instance, when you need to unload the whole trailer and take the pallet somewhere and then again, and like that the whole day, and tomorrow you wake up and do that again. So I mean, it's the 21st century. We shouldn't have to do that, and we should really use robots to automate these tasks. So basically, here you can see a tray, our autonomous forklift. So it's used for unloading and loading operations on trailers, and Casey, our case picking solution. So since I'm working on tray, and it's kind of my favorite child, I'm going to first show you the video of the tray. If it please. Sorry, guys, for this. Can you play it from the... Okay, no. That's a disappointing, really. Okay, so what does the autonomous stack that powers our robots look like? So we start from sensors. Here you can see our stereo camera, our proprietary vision module, which is used to capture images. Then in the next layer, which is semantics, we use neural networks to really process these images. And then what's really interesting, and I think really cool, is that we do not use neural networks only to, I don't know, detect objects, perform semantic segmentation, and all the stuff that we are really nowadays used, that we use neural networks to do them. We also do use them for localization in mapping, so we do not rely on GPS. And when we have the maps of the environment, we can plan trajectories and navigate through the warehouse. And also, I think that it was mentioned earlier in the keynotes today, it's important for us, or for our robots, to really adapt to the environment. So if a person steps in front of the robot, or a box falls into the robot needs to stop, replan the trajectory, and go around the person or the load. So actually, let me tell you more. So first, here you can see our proprietary vision module, our stereo camera. And it's developed fully in Gideon, both hardware and the software stack for it. And you might ask yourself, so why didn't we use some kind of off-the-shelf stereo camera? I mean, there's plenty of them. The thing is, when you deploy the robots in the wild, you need them to work really in all kinds of warehouses, no matter what kind of lighting is installed in the warehouse. So also, picture that you're unloading a trailer. So it's pretty much dark in the trailer, and you need to be able to see in the trailer. So that's why we equipped our camera with a premium global shutter image sensor. And we also have wide lenses to ensure maximum field of view. I think it's also important to have 360 degrees field of view so that you don't have any blind spots. And that's why we designed our stereo camera to be extendable to a multi-stereo camera system. I mean, it's also really important to have multiple cameras when you start doing localization and mapping, so SLAM. So having multiple cameras really helps. So once we captured the images, we parse them with neural networks. So one of the tasks that we perform is semantic segmentation. So for each pixel in the image, we determine, okay, this is a floor, these are the pallets, this is the cargo, and stuff like that. And I think what's really important here that our neural networks need to be run on limited hardware. So first of all, they need to be designed to be able to run on such hardware. So we need to have efficiency and accuracy at the same time. And these are like, it's almost like training again. You have a min-max gain to optimize here. So, first we design them to be efficient, and then we also perform various kinds of tricks to really make them efficient on the hardware after the training. So after the semantic segmentation, there are also two really important tasks. So for instance, if you want to manipulate the pallets, you need to be able to distinguish the instances. Okay, so this is the first pallet, this is the second pallet, and this here in the back, I don't know if you see it, is the third pallet. And so we have bounding boxes, but actually bounding boxes are really not enough. We need to have like precise instance masks. And so for that purpose, we also use instance segmentation. And well, all this is very cool, but I mean, having these bounding boxes in images will not really help the robots to take the pallet and move it around. So to do that, I think what I really found interesting about this job is you really have to move from this 2D space of images into the 3D world, because we live in a 3D world. And for that purpose, so for a robot to really come to the pallets and take it to the trailer, we need to estimate the pose, like 3D pose estimation. For instance, we need to know that robot needs to rotate for 3 degrees, move 3 meters ahead and half a meter to the right to really pick up this pallet and take it to the trailer. And also, since I noticed neural networks, so what was really mentioned in the first keynote today is that we as humans need only a few samples to be able to learn some kind of visual concept. So there have been a few academia approaches to a few-shot learning. I personally think that it's super cool and interesting topic, but I mean, we still need to have significant amounts of data. So we have our in-house data collection team, which goes around with the dataset collection kit and collects the images for us. And what's really important, we really monitor the performance of the model in production. So we immediately detect situations where the model does not perform as we would want it, and then take these images into the training set, retrain the model, and reiterate. And we also have an in-house data annotation team that annotates these images. As I mentioned, we live in a 3D world. Basically, we need to estimate distances. So how far is this building? How far is the car? How far are the other objects in the image? So for that, we use our stereo cameras, and actually depth estimation by itself is performed on the stereo camera itself. The problems that we are facing here are classic, like reflective surfaces, featureless surfaces, for instance, walls and stuff like that. And here we also use neural networks coupled with traditional approaches. So what kind of data do we use to train stereo? We use public data sets, also self-supervised methods, and also LiDAR. Okay, so I already told you that we do not use neural networks only to process images. We also use them for localization. So when each one of us, someone tells you navigation, mapping, we instantly think of GPS. So we do not use GPS. Because why? Because it's not really precise indoor. I mean, you can install an RTK antenna, but this by itself holds a set of problems. We here also rely purely on images. I mean, when you think about it, it's the way that we humans do. So yesterday when I was in Grafički Collective, and I decided to walk to my hotel. And then I knew, okay, here is Nacionalno pozorište. It's a huge landmark, so I need to make a turn here. So this is the way that we humans do, that we navigate. We look for the features in the environment, and or to say so, for landmarks. So this similar approach is actually applied in visual localization and visual SLAM. So basically, so here on the slide, you can see the results of the dense reconstruction. So it's really like 3D reconstruction of the world. So we take the depth maps from the stereo camera that I've shown you just before. From then we can obtain point clouds. And also you can see here that all these surfaces are really nicely colored. For that, we use semantic segmentation maps to really give the semantic meaning. So we know that this is a floor, we know that this is a pallet stand, and stuff like that. And also, if you noticed, there are no moving objects, because, I mean, when you're creating a map, you don't want to have moving objects in the map because they're not useful for navigation. I mean, this moment they're here and the other moment they're not. So basically, when we're performing mapping, we don't want moving objects in the map. And for this purpose, we also use semantic segmentation for that. And so now, say that we have a map of the environment. So how do we localize in it? So for instance, say we built like this really, really nice map. And then we came a month later and we're driving to the warehouse and we really want to quickly determine where we are. This is done on the image level to really be efficient. So to say on a coarse level. And we also use neural networks for that purposes. So to extract image level features which would be useful. So to quickly, roughly estimate, so I'm here in the map. But obviously, having these rough estimates, it's not really enough. And I mean, you want to be able to precisely determine where you are. So we want to estimate on a fine level where we are. So say that this is the image that robot is seeing right now. So the surroundings of the robot. And this is the image from a few moments before. And so the goal here is to estimate how much has the robot moved. So it moved for 3 meters, it rotated, I don't know, for 2 degrees or something like that. So how do we do it? So if we extract salient features from images. So for instance, okay, when I would have to determine as a person, okay, I see this corner here on a palette and I can easily identify one such corner on another image. And I think what's really important to note here is the context. So how do you match the features which are on the wall? Wall is a featureless surface. So how do we do that? So for instance, how would I do it? So I would look, okay, so this feature is at this distance from this palette stand. So we look for context. And one really great method to take the global context into account are transformers. So we also used transformer-based architectures for this task. So we do train neural networks, obtain these matches, and then from that we can estimate the camera movement. So basically, how do you train this stuff? So we cannot rely on our annotation team. So for instance, picture if you had to annotate all these key points, say you don't have to annotate a lot of them, like 10 of them only. And you need to track them like for 30 frames. I mean, this would really quickly become infeasible. So we cannot really rely here on human annotation. I think that this is also like an interesting problem. How do you get data and you don't have data? And also public data sets are also often used only for academic purposes, and you cannot use them. And maybe they would not generalize really well to warehouses. So the idea here is to use like a pseudo supervision, to use structure for motion algorithms to really obtain the training data for our neural networks. So, I mean, I've talked a lot about now the indoor environments. So the challenges in indoor environments is, so when you come to, I don't know, in Croatia, in Atlantic, so you come to a warehouse and then you come on another day and the warehouse looks completely different because they moved everything around. So everything is moving. The pallet stands are moving, people are moving, forklifts. So it's a highly dynamic environment. So this is really the challenge here to identify the static scene features, so which can then be used to estimate our movement. But we also deploy our robots outside. And I think when we are talking about SLAM and localization outside, this is also a challenging and a hard problem. So for instance, you have seasonal changes. So like vegetation loses leaves in autumn and in winter. So you have snow in winter, right? So you have day and night changes. Also, is it raining, snowing, and stuff like that. And I mean, the environment is also constantly changing. So when I was in Belgrade 2 years ago, it looks quite different. I mean, the city has built a lot since then. So all of these are challenges that we need to solve if we want to solve them with vision. So, I mean, the question is, can it be solved? And we argue that it can. So one thing and one really nice demo, which I would like to show you, is that the one of mapping and localization. So we created a map on a really sunny day. We came with the robot on a parking and really created a nice map. And then we came a month later with a different robot. It was evening and it was raining. And the robot was able to successfully localize in the map. Despite that it was raining and the surroundings look quite different. So basically, here you can see, this is the image on a rainy day. So you can see raindrops on the camera. And this is like the image which was captured on a sunny day. And you can actually see the matches between the two images. And here you can see like the 3D map and the robot like reconstructed 3D point clouds and matches that the robot is like really really performing and is able to correctly localize in the world. So unfortunately, this was like a really nice video, which does not play. So all this that I've shown, I didn't do it by myself. It's actually a joint work of 70 people. I mean, currently there are around 130 of us at Gideon. Some of them are working on autonomous stack, and some of them are working on hardware. And we are always looking for talented people interested in AI, in computer vision. I think that it's really cool, and if everyone wants to chat, I'll be here for the remainder of the afternoon, so feel free to stop by and chat. And with that, I would like to conclude my presentation. So if you have any questions now, I think it is, I really had a lot of videos, which unfortunately did not play, so
we'll check it out. So any questions? I barely can see if... Yeah, here's the question. Can we get the mic, please?
My name is Mikhail Roshkov. You mentioned that you cannot rely on data annotation team. Mm-hmm. So it seems that sometimes you have errors in annotated data, mm-hmm. right? So my question is, how do you manage these versions of annotations for data sets and how it affects the model training process?
Mm-hmm, mm-hmm. So when I said that we cannot rely on our annotation team, is for a specific purpose of visual localization. So for the task of visual localization, there you would have to annotate particular features in the image, so in one image, and then you would have to find, okay, this is the corner of this chair in another image, and so on. So this is like really infeasible. So for me, if I would have to do it and I train these algorithms and I really like my training data to be clean and everything, after 2 hours of doing that, I would quit. And I mean, it's not feasible in that way. But to answer your question in a general case, so we have an in-house annotation team, and we also have a quality control. So each image that gets annotated is like really reviewed by other annotators. So we have a consensus on that. So we did have problems that you mentioned before, but I mean, to really adapt to all different kinds of warehouses and everything, we really needed to solve this problem to be like production ready. So I wouldn't say that it's a problem right now.
Okay, thank you.
Thank you.
Any other questions? I mean, could it work in any warehouse, or you have to prepare it to get it into the warehouse? I mean, do you have to prepare something before you put tray into the warehouse?
I mean, it's the holy grail, like the generalization problem. You always want to generalize. And yes, we do some kind of screening of the facility before, capture a few images. But what I would personally like to say that I'm really like happy about, and we just recently reached this stage of maturity, that our really pose estimation model generalizes quite well to the palettes that we haven't seen before. So it's a completely new type of palette, and the model has really learned to identify where are the key points on the palette. So yes, we do prepare, but I would also say that our models are really now trained well and that generalize well.
So in theory, if there is a warehouse that is dangerously polluted and you cannot put people in it, so you have to bring in your tray to move things around and, you know, to help it clean or whatever it has to be done. It can do that task.
Yeah, I mean, for me personally, the greatest challenge here is not to eliminate the people from the equation. but to work side by side with humans. And this is like really, so
But sometimes you cannot get people in a polluted place because
Yeah,
if
yeah.
let's say that there's a
Yeah.
chemical that was spilled all around.
yeah. But I mean, commercial applications that we are deploying Tray now, there are people in the warehouse, and we really need to be have zero margin of error here. So if a person steps in front of the tray, it needs to stop. And also, I mean, we cannot allow ourselves to damage any cargo. And so it's like we need to be fast enough. And on the other hand, we need to be performing in a safe and responsible manner, really. So,
Okay. Thank you. Thank you for
Thank
this.
you.
That was Valentina Zadrija.